Warning: sodium hydroxide and sodium methoxide are corrosive. Chloroform is carcinogenic. Wear gloves when handling them. Methanol is highly flammable. Fire safety protocols should be in place. Greetings, fellow nerds. In this video, we're going to make Trimethyl Orthoformate. Now, it's a rather unusual organic reagent, so first a bit of background. The classic carboxylic acid group has carbon to which there is a double bonded oxygen and a single bond hydroxyl group. Now, in theory, if you could react this with water, you would get a carbon bonded with 3 hydroxyl groups. This would be called a carboxylic orthoacid. Now, as far as I know, these have never actually been made or detected. And even if they could be made, they would be incredibly unstable and quickly decay back into carboxylic acid and water. Now, we know that if we condense the hydroxyl group of a normal carboxylic acid with an alcohol, we get an ester. This is well known in chemistry and done every day. We ourselves did this in a previous video. If we went a step further and did this to our hypothetical orthoacid on every hydroxyl group, we would get orthoester. Interestingly enough, this stuff can be made using a roundabout procedure, and we're going to do just that in this video. We're going to focus on making Trimethyl Orthoformate because I want to use it to make an antiprotozoal drug. It's also the simplest of the orthoesters and is thus a good demonstration reaction. It uses the simplest carboxylic acid, which is formic acid, and the simplest alcohol, which is methanol. To start, get 200 milliliters of methanol and add 40 grams of sodium hydroxide. Then we start until completely dissolved. This might take a while as sodium hydroxide dissolves very slowly in methanol. What we're trying to do is make sodium methoxide. But this reaction doesn't go to completion since it's easily reversible as the water reacts with the sodium methoxide again. Professional labs make sodium methoxide by reacting sodium metal with methanol. This avoids the water issue entirely. But obviously this reaction is very dangerous since the methanol can easily catch fire. Sodium metal is also somewhat difficult to obtain domestically. To force the equilibrium to the right, we add 100 grams of molecular sieves 3A. Make sure they were previously dried per the manufacturer's instructions. Now seal up the flask to prevent the evaporation of the methanol, but more importantly to prevent moisture getting in. Now mark off the starting level of the flask and let it sit for a few days. As demonstrated in a previous video, molecular sieves are very good at removing water from solvents. By pulling the water out of the system, we force the equilibrium toward the formation of sodium methoxide. As this happens, the liquid level will go down as the water is removed. It's pretty slow, and I'm time-lapsing this video over 24 hours. Every day, give the flask a good shake to prevent dead pockets of molecular sieves. Now, when the liquid level stops decreasing over a 24-hour period, we're ready to use a solution of water-free sodium methoxide and methanol. Now set up a flask and stir bar with a vertical condenser column for reflux. I should emphasize at this point all subsequent apparatus should be meticulously dried before use, preferably in an oven. Any water that comes in contact with the reaction will destroy the Trimethyl Orthoformate we intend to make. This is because orthoesters are very water-sensitive chemicals and irreversibly react with water to release their alcohols and normal esters they are made from. So be as dry as you can. Now transfer the sodium methoxide solution to the reflux flask. Try not to transfer any of the molecular sieves, but a few pellets is not a problem. Now turn on the cooling water and start heating the mixture until it starts to reflux. When it starts refluxing, turn off the heating and get 30 milliliters of chloroform. We made this chloroform in a previous video on the haloform reaction, and it's also been dried over molecular sieves. Now add the chloroform 1 milliliter at a time through the top of the condenser to the hot sodium methoxide solution. Do not add it all at once or the reaction will go into thermal runaway. Add in at a rate to maintain constant reflux. The reaction is very exothermic and will boil quite vigorously with every addition. What's happening is the chloroform is reacting with sodium methoxide to produce trimethyl orthoformate and sodium chloride salt. The sodium chloride has low solubility in methanol and precipitates out as a white powder that you can see here. Now, even though the reaction is very exothermic, we start with hot sodium methoxide solution because the reaction proceeds very slowly at cold temperatures. The false sense that the reaction is under control can lead you to add more chloroform than the apparatus can handle, and when it does start up, the self-heating leads to thermal runaway. I'll admit I made this exact blunder and spent my Christmas cleaning my fumid of the resulting chemical waste. Anyway, once all the chloroform has been added and the refluxing has stopped, turn the heating back on and reflux the mixture for 1 more hour. This is to ensure the reaction is finished. Then let it cool to room temperature. Now we need to remove the salt, so to do that we vacuum filter over a fitted funnel. Don't take too long though, as the Trimethyl Orthoformate is being destroyed by the moisture in the air. Here is our filtrate, around 150 milliliters worth. To recover the small quantity of trimethyl orthoformate, we use fractional distillation. We're going to do this in two phases, with the first one using the full-size 2440 fractional distillation setup. What boils off first under 60 Celsius is an azeotrope of methanol in excess chloroform. This azeotrope has a boiling point of around 53 degrees Celsius. Then we boil off the next 100 milliliters of methanol at around 64.7 degrees Celsius. We're not going to boil down all the way to the trimethyl orthoformate because even with perfect yield, we're expecting only 36 milliliters of it. The sheer size of the full distillation setup means that there's a lot of dead space the product must fill first before it can distill over. Our recovery would be terrible if we got anything at all. Professional chemists solve this problem using a chaser solvent, also called a pusher solvent or tail solvent. The chaser solvent is a very high boiling liquid that distills last. As we get down to our product, which is now the second last liquid, the chaser boils and fills the dead space in the distillation apparatus, pushing out the product. Since the boiling point is much higher, it's easy to observe and separate, and only traces end up in the product. I didn't do that for this procedure because for a very sensitive chemical like trimethyl orthoformate, the chaser solvent must itself be meticulously purified and dried, so it doesn't destroy our product. I wanted to see how far I would get without a chaser solvent and if the yield was usable. Now after distilling off most of the methanol, we now stop the distillation and let all the apparatus cool. Here's residue containing the side product, decomposition products, sodium chloride byproducts, methanol, and our trimethyl orthoformate. This much smaller volume of material means we can now transfer over to a much smaller 1420 size of distillation apparatus. Being smaller, there is much less dead space than the full-size apparatus. You'll notice I'm using an unconnected condenser column as a fractionating column. As I said before in my fractional distillation video, you can use an unconnected condenser with some loss of performance. Fortunately, the boiling point of trimethyl orthoformate is much higher than methanol, so even this condenser should be able to give a good separation. Now start the heating and there it goes. First, methanol will distill over. Trimethyl orthoformate boils at around 101 degrees Celsius, so when the vapor rises above 75 degrees Celsius, change out the receiver and start collecting the product. And there it is, trimethyl orthoformate. I only managed to get 7 grams of an expected 35 grams for a yield of 20%. While this is very low, I think it's easy to fix by using even more molecular sieves from my original preparation of sodium methoxide. I think the original sodium methoxide was not as dry as it could be, and using extra molecular sieves is a cheap and easy solution. Also, maybe I should consider using a chaser solvent to squeeze out the last drops of product from the distillation apparatus. Nonetheless, for a successful run, I think this was pretty good. Now some of you might wonder why I didn't use magnesium and react it with methanol to make magnesium methoxide and in turn react it with chloroform. I actually did try that at first, but I got no yield at all. So I had to use the sodium hydroxide and molecular sieve method. Now orthoesters are used in organic chemistry to make acetals from carbonyl groups. I'm going to try and use this to make an antiprotozoal drug. Thanks for watching, and remember to add the chloroform slowly so it doesn't go into a thermal runaway like my not so successful attempts. If you would like to support the continued production of science videos like this one, please support the channel on Patreon. Links are in the video description.